Hi, I'm Bruce Hemp, Applications Engineering Section Leader for Linear Technologies RF Products. This presentation is about how to design a 3.6 GHz dual-channel receiver with 100 MHz bandwidth and a robust level of performance suitable for base station applications. Let's look at the LTC 5566. It is a dual-channel mixer integrated with a pair of programmable gain IF amplifiers. Both mixers have wideband RF input and LO match, allowing the mixers to operate from 300 meg to 6 GHz. Each mixer has plus 25.5 dBm input IP3 at 3.6 GHz, which is quite good input third-order intercept performance. A single LO input at 0 dBm drives the two independent LO buffers to ensure coherent phase and provide about 50 dB isolation between the two channels. The chip utilizes a serial peripheral interface bus, SPI, that provides 5 bits for setting each channel's gain independently in 0.5 dB steps. The total power conversion gain range is from about -4 to +12 dB, as shown here by a family of response curves. Notice the RF frequency response is quite flat from 1.6 to beyond 4 GHz. And for our design, we will use 3.6 GHz. The SPI bus also allows you to fine-tune the RF input impedance matching across 3 overlapping frequency bands from 1.3 to 5.1 GHz, simplifying the implementation of software-defined radio applications. Extending the RF frequency range down to 400 MHz or up to 6 GHz is possible by modification of 2 external reactive matching elements. Setting the RF tuning bits to 00 yields better than 10 dB return loss at band 0, which covers 3.1 to 5.1 GHz. Setting the RF tuning bits to 01 shifts the optimum matching down to band 1, which covers 1.8 to 3.8 GHz. And so on for band 2. To get to band 3, which is 650 MHz to 1.3 GHz, a shunt inductance of 8.2 nanohenries is added. And for band 4, 10 nanohenries is used. Now let's look at the cascaded system performance in a 3.6 GHz, 100 MHz bandwidth MIMO receiver application. In list chain analysis, we chose 30 dB of LNA gain and a couple of 100 MHz bandwidth RF bandpass filters in front of the mixer. We max out the mixer gain to 11.8 dB and also add a bandpass filter at the IF, allowing for 5 dB of filter insertion loss. This is a very basic receiver implementation. The cascaded receiver has reasonably good noise figure of 2.1 dB and a total cascaded gain of 33.8 dB. The receiver input IP3 is approximately -4 dBm. The cascaded output IP3 is plus 29.8 dBm, ready to feed into an ADC. If more gain is needed, simply add gain at the mixer IF output. This should be a high linearity amplifier, as it will affect the linearity performance of the receiver. Here, we added a LTC 6430-15, which has plus 50 dBm output IP3 as the last IF amplifier stage. Because of the added gain, we backed off the LTC 5566 gain by 6 dB. Now the total receiver gain increased by 9 dB, providing ample drive to the ADC. Notice the input IP3 holds at about -4 dBm with negligible noise figure increase. In the final system implementation, the down-converter gain can be fine-tuned for best performance for a given configuration of antenna, site conditions, choice of ADC, etc. The LTC 5566 is designed to handle +5 dBm nearby blockers, which translates to about -22 dBm at the antenna. And the maximum input signal level is assumed to be at least -35 dBm. This combination makes for a very robust receiver. In summary, a high-performance 3.6 GHz dual-channel receiver can be implemented that will support more than 100 MHz bandwidth and is easily scalable to 4, 8, or 16 simultaneous receive channels, such as in a remote radio head. And the receiver can handle strong nearby blockers. Integrating the dual mixers and IF variable gain amplifiers makes for a low component count solution that is small size and cost-effective. For more information, please visit linear.com. Thank you for watching.